We now take up an example of the verification of Green's theorem in the plane. We will verify it for particular choices of P and Q, which are each functions of x and y, and for specific choice of C, the closed contour over which this is evaluated, and C is defined in this particular case that we are going to tackle. C is consisting of C1 and C2, where C1 is given to be the curve y is equal to x square and C2 is the curve given by y is equal to x. The choice of P and Q is also trapped or captured here. This is the specific choice of P xy and Q xy that we have captured. So what we will do is we will quickly rub out a part of the board and draw a diagram. Again, I re-emphasize that drawing a diagram properly is essential to solve these kind of problems. Otherwise, things might take a very sharp tangential turn if the diagram is not correct. Here, of course, I have taken simple curves which are easy to draw, and we will do just that. So we leave the definition of the curve here, we leave P and Q there, and rub out the rest of the board to create working space. Since we are going to need the del q del x and del p del y, it's better to just do it right now and store it somewhere on the left. Now del q del x is the del x of this, and that is 2x. Clearly, in this case, del p del y is the differentiation of this with respect to y, so it will be x plus 2y. Del p del y is nothing but x plus 2y. We will keep this in this part in reserve. Now let us draw the contour C and see what is the area R. You know, the line integral is evaluated via a double integral, and ultimately the verification consists of showing that the line integral for any choice of P and Q and the double integral, they are of the same value. So the curves are like this. This is C1, which depicts y is equal to x square. It is a parabola whose axis is parallel to the y-axis. This is the y-axis and this is the x-axis. Similarly, C2 is y is equal to x. This is a straight line with slope of 1. So we will start at the origin, passing through the origin. It passes because it is of the form y is equal to mx plus 0. With m is equal to 1, we draw a line that is 45-degree inclined. There. This point will have to be found out by solving the two equations, the two curves simultaneously. So if we square this, or x is equal to x square, we just equate x is equal to x square to find this point P. For P, what we do is we equate x to x square, and this implies x square minus x is 0, which implies x into x minus 1 is 0. So either x is 0 or x is 1. X is equal to 0 is reflective of the fact that the curves intersect at the origin. This is one point of intersection. They both start from there in this particular case, and x is equal to 1 is this point. When x is equal to 1, because this point lies on the line y is equal to x, the y coordinate of that point will also be 1. Hence, P has a value or has coordinates 1, 1. That is the curves. This is C1, the lower curve, and this is C2. So we'll first evaluate the line integral P dx plus Q dy over the closed contour that starts from here, goes like this, reaches this point and gets back here. So that is a depiction of a counterclockwise travel. We'll evaluate that integral in steps. So now we can afford to rub out this part, and even because the whole thing has been captured in terms of a sketch, we can even erase this part so that we get space to evaluate the integral. Step 1 is to find P dx plus Q dy over C, and this is the closed contour C. Now, since C consists of C1 and C2, and C1 is this one, we first evaluate P dx plus Q dy over C1, and then from this point to this along C2. Over C1 means along C1. Now, step 1, along C1. Mind you, here it's not a closed curve because C1 is not a closed curve by itself. So we don't put that circle and the arrow. P dx. P is xy plus y square. Plus Q x square dy. That is it. So we'll have to evaluate this. That is P dx plus Q dy evaluated on C1. Now on C1 we can see that y is equal to x square. So we can convert this integral in terms of x alone, and we can write x square as y here, so that this integral gets converted to in terms of, we can also convert it in terms of x. If y is equal to x square, dy can be written as 2x dx. So ultimately this works out to, on C1, x, y is x square, so x cubed, plus y square is x to the power of 4. Y being x squared, y square is x to the power of 4, that's fine, plus x square into 2x dx. So 2x cubed whole thing dx. This has to be understood very carefully. What we've done is we've replaced y by x square for C1, and here, that is x square dy, we put as in terms of x. Y is x square on C1, dy is 2x dx. So the entire integral now is a single integral from single in the sense that it is in terms of x alone. So we now need to set the values of x for C1, and that is actually 0 to 1. So we can write this as 0 to 1 and integrate term by term. First is x to the power of 4 by 4 integrated between 0 and 1 will be 1 by 4. X to the power of 4 can be integrated to x to the power of 5 by 5, and substituting the values, it will be 1 by 5 plus 2x to the power of 4 divided by 4, so half x to the power of 4. So plus half. All this is 25 plus 4 plus 10 is 19 by 20. Is the value of the first line integral. We'll now do the second line integral. That means from this point to this point along C2, and mind you, it's very important to see that in the anti-clockwise traverse of the entire contour C, we are going like this and then from here to here. So if we were to put the limits for this particular integral, the x limits would be from 1 to 0, not 0 to 1. That is for C1. So we store that result 19 by 20. Along C1, the result is 19 by 20. Then we do it for C2. Step 1 still continuing. Second part. Step 1, we can now write continued. So that is integral along C2 p dx xy plus y square q dy x square dy. Again, on that curve we have y is equal to x, so dy are the same thing. So this can be written as C2 x, y can be replaced by x because on that curve y is equal to x, plus y square, that will be x square dx plus x square dx, because y is equal to x on that curve implies dy is equal to dx. So capturing these together, we have 3 x squares together, and the limits are now from 1 to 0. So 3x square integrated from 1 to 0, we will get 3x cubed by 3. So just x cubed. This is x cubed. Between limits 1 and 0. 1 and 0, and that will be 0 minus 1. So this evaluates to minus 1. So along C2, the result is minus 1. The sum of the integrations now, starting here, going here and getting back, is the sum of these two, and the result is minus 1 by 20. It's negative, does not matter. Minus 1 by 20, it's fine. That should not pose any problem. We now integrate to find the double integral over R, that is the region trapped between these two curves, of del q del x minus del p del y for suitable limits of x and y. We rub out the earlier parts. This calculation can be rubbed out now. So the next step is evaluation of the double integral. Evaluation of the double integral. We now proceed to evaluate the double integral del q del x minus del p del y dx dy by the definition of double integral, whatever we know. The region is this one, R. This is our R, trapped between C1 and C2. Now we have done this earlier. Del q del x is 2x, del p del y is x plus 2y. So once we subtract del p del y from del q del x, we will get 2x minus x is x, and this will become minus 2y. So this reduces to R x minus 2y dx dy. So that is the only task left. We know that our contour integral was minus 1 by 20, and now we have to evaluate this double integral. We can now afford to rub out this part because we don't need this anymore. So we'll use that space to evaluate the integral. We know to set the limits for this, we have to take the limits for y lower curve to y upper curve, and x will be the leftmost value of x to the rightmost value of x. The region is now defined by this integral, is simplified by writing dx x is equal to 0 to x is equal to 1. So leftmost value of x is 0, the rightmost value of x is equal to 1, and this x minus 2y dy, where y will vary from the lower curve, which is y is equal to x square, and the upper curve is y is equal to x. So if we can evaluate this, we should be home, and the resultant should be equal to minus 1 by 20. Let's see. Sorry, this mic fell off. So this integrated with respect to y is, we keep the limits, x is equal to 0, x is equal to 1 dx. Now we integrate this with respect to y. This will integrate to xy minus 2y integrates to y square. And y has limits x squared to x. This is equal to x0, x1 dx. First we put x as y as x. So this is x square minus x square, that is 0. Then we put this value. So minus x to the power of 3. If y is x square, this becomes x to the power of 3. This becomes x to the power of 4 with a minus. So we can take the minus out. So this is minus is out, 0 to 1, integral of x cubed minus x4. Is minus of, this integrates to x to the power of 4 by 4. So 1 by 4. This is 1 by 5. So that is 5 minus 4 over 20 with a minus sign. So this is also equal to minus 1 by 20. And we are therefore absolutely home because these two values are equal, which we expected, and that is the prediction of Green's theorem in the plane. The contour integral over C is equal to the double integral of the function, whatever p and d, del q del x minus del p del y, over the region that is defined by C1 and C2 in this particular case. Thank you.